Guys, if you've understood the previous lesson, you can just purely skip this lesson. This lesson is only for those that really want to go into, a deeper understanding of the problem of the sphere, finding the volume of the sphere, and really see what we can come out of it. It's just a short lesson, so if you want to just watch, it's okay. It's just something that I thought of after I finished the first lesson, so I thought I just want to share with you. Alright, so basically what we just had is that we had the volume of the sphere. What we did was that we find the equation of the region R in terms of polar coordinates and then just apply the theorem, okay, bearing in mind that we need to multiply the function in terms of R. So let's just look deeper into this problem. Now this, like I said, is again the surface, correct? It's the surface. And I also told you that when we arrange this, what we have is essentially z squared equals to a squared minus r squared, and we could write that as square root as a squared minus r squared, okay, or minus the square root of a squared minus r squared, because this would give us the surface that's above and below. A brief explanation is because when we pick a point, we need a unique value on the surface. So the value is either on the top or it's at the bottom. Alright, so let's just take a stab at this. And what do you think if we applied the double integral formula in polar coordinates to both this? Okay, let's just reach a common consensus first. The common consensus is that in order to find out the function of the surface, right? So the function of z, okay, we need to definitely take the square root. There is absolutely no way, or at least for our level, to put this equation inside the function. Okay? Again, what is a function? A function must give us one value of z in terms of r or theta. Theta is not here because it's independent, so we put in a value of r, we need to get a value of z. So it's a common consensus that this does not make sense in terms of using the double integral. Okay, this is again, I guess I can talk more about this, because when we get a certain function of the surface, right, we must make sure that it's written in a form like this: z equals to the function r and theta. Okay, so that's what we did here. Okay, so there is no denying about that. So what we'll do is that we'll try to apply this formula into this equation over here, knowing that now we have explicitly, okay, defined the surface z as both the one above the xy axis and the one below the xy plane. Sorry, the xy plane. So now what we have is something like that. Okay, not much of a sphere, but it's alright. So this is going to be z equals to negative a squared take away r squared. Alright, so let's just apply the double integral. So I will just write volume is going to be equals to, the first one is the one on top. Okay, so double integral over the region R of the function a squared minus r squared dA. Okay, yes, I know I did not multiply r inside there because I still stick with the initerated integral. So it's still, the general form, okay? It's not iterated yet. And then after that, what we'll do is that we'll plus, okay, the double integral. So what we will have to plus, basically applying the double integral for the surface at the bottom, right? Okay, so that'll be region R minus, okay, a squared minus r squared, okay, dA. Okay, and then what we know about, rules of integration is that this can be written as subtract double integral over the region R of a squared minus r squared dA. Basically, it's just bringing out the constant, okay? Now, we will see that, this quantity is exactly the same as this quantity over here. Okay, it's just that there's a minus sign now. So, you could use the iterated integral, apply the limits of the region R, do the calculations, but what you will get is that you will see that this volume is going to be exactly the same as this volume. But it's just that now there's a minus sign, so the volume is going to be equals to 0. Okay, now, avoid a mistake that if you want to make, that is why if you notice that our first definitions, we have always said that the function R function of r and theta is always more than or equal to 0 for all points r theta in R. See, all these conditions in mathematics, we need to look at them, read the mathematics carefully. This case does not apply. This surface does not satisfy this. That's why we get all these strange results. But if you just look at it with your analytical mind, you will see that it does make sense. Okay? Why does it make sense? Well, simply because the double integral gives us the net sine volume. Okay, just like the double integral in rectangular coordinates. What is the net sine volume? It's basically the volume above the xy axis. So for this one, what we got, it was 2 divided by 3 pi a cube, right? What we have over here is 2 divided by 3 pi a cube, which is the magnitude. But remember, since it's the net sine, there's a sign to it, it's going to be negative. Why? Because it is below the xy axis. So if this minus this, what we get is equals to 0. A way around this was to take the magnitude and then you add it up, but that's besides the point. What the point is that make sure that when you define the surface of z, knowing that you need to write z explicitly in terms of r and theta, make sure you know whether is it above or below the xy axis to prevent any of these strange results. Mathematically speaking, it is correct, but geometrically speaking, you know, it doesn't really make sense. How can the volume equals to 0? Alright, last thing, and a rather interesting thing, okay? Let's see whether we can solve this problem without sketching r. Okay, I kind of like that, and let's just, you know, go right to it. So remember, how do we get the surface r in this case? Well, basically because, you know, we know that the surface of the sphere, you know, kind of cuts the xy axis. What we did is that we let z equals to 0. Let z equals to 0 to get basically the equation of, you know, this thing over here, which ends up to be our equation of r, region r, because, you know, that's on the xyz axis where z equals to 0. So what we have is that r squared is equals to a squared. Now what we can say from here is that r is equals to a. Okay, so this tells us that the radius of the region R is always equals to A. That is important because what we know about that is that immediately we know that it is a circle. Okay, now I know I'm graphing it out, and I know we want to see a non-graphical solution, but you know, basically that is what we mean. So this would give us the limit for R1 and R theta. Okay, does that make sense? R1 theta and R2 theta, because we know that since the radius is always equals to A, you know, it's always going from here to A, and it's always A. So the outside region R2 is always A, we're always going to start from 0. So this one is correct. Okay, now what about alpha and beta? Now this one takes some thinking. Remember, we are using an algebraic solution to find the limits of the region R. This will come from over here. What do we know about R squared? What we can say about R squared is that R squared is equals to x squared plus y squared, and this is of course given equals to a squared, right? We know that. Now what do we know about this? Well, we know that this is going to be r squared cosine theta, r squared cosine squared theta plus r squared sine squared theta, and this is going to be equals to a squared. What do we know about A? A is given, R is always equals to A. So basically we can change this to A squared theta. And then we cancel that out. What we have is cosine theta plus sine cosine squared theta plus sine squared theta equals to 1. Okay, now this is, I'm going to stop right here. Okay, reason being, we need further skills of trigonometry to really find the angle of theta, because somehow we suspect that these two angle thetas will correspond to the angle alpha and beta. We suspect, we don't know for sure yet, but we can highly anticipate that because, you know, we work through the algebraic mathematics. But what can I say about here? I can say that this statement is true is theta equals to 0 or theta equals to 2 pi. Okay, and this is why alpha becomes 0 and beta becomes 2 pi, because this would satisfy our initial conditions when we had the theorem of the double integral. Beta is more than alpha, and basically this is going to be always greater than r equals to 0. And that is what we have. Looking at the equation of the sphere, knowing when the surface is above, below, knowing how to somehow predict using algebraic methods the limits of R, you know, because R could be highly complex in most cases where we can't graph it out. And then obviously, you know, see something out of that. Okay, not much to it, you know, basically just supplementary to the previous problem. And you know, if you enjoy it, that's good, that's good. Always be interested in the mathematics and know all these conditions, all these small little, you know, glitches that may crop up. Okay, next lesson coming up.